floor to Mark Kedzier to introduce our guest speaker and chair the program. Take it away, Mark.
Thank you, Madam President. I was mentioning to Jonathan right before I got up here about I feel a funk in the room, and I think it's like everybody's having total solar eclipse withdrawal. You know, I'm sure you do that because everybody was so geared up the entire year. Now we're back on. Everybody come on down. We're just going to do some regular astronomy, like Mr. Ross was talking about.
Yes, life goes on after the eclipse.
That's right. Life goes on. That's it. Okay. Anyway, it's my pleasure to introduce our speaker. This will be part 1 of 2 that she'll be doing. She'll be here again next month, right here in this room. And let me give a little biographical information on her that she provided for me. She is a lifetime member of the San Jose Astronomy Association. She's a current member of the Ford Amateur Astronomy Club. Do you still have your 14.5-inch Starmaster? All right. Starmaster telescope, she got that in 1999. She worked at Lick Observatory in public outreach for 10 years from 1997 to 2006. She worked at NASA Meteor Shower Studies for 7 years from 1996 to 2002. She's a Starry Night Supervisor at the Wayne Oakland Science Olympiad since 2014. She has a Meteorite Tektite collection of over 100 pieces. And she does public outreach with her collection of schools, scouts, MSC, what's MSC? What's that?
Michigan Science Center.
Michigan Science Center, Astronomy at the Beach, Astronomy Clubs, and other public events. And her presentation tonight will be on meteorites and tektites, the types and composition, and this will be part 1 of a 2-part presentation that she's doing. And without further ado, I'd like to welcome Sandra Macika from Ford.
Hi, thank you for having me today. So I will get started then. This presentation, unfortunately, I forgot to bring my presentation with me, and my friend saved me. He emailed me one that I had sent him recently, and so there's a few updates to it that I've made recently. My total collection at this point is, I think, 73 meteorites and 33 tektites, so just over 100 pieces. And today we're going to just talk about meteorites from differentiated planets, and go through and explain what all that is. Oops.
You can just click the button. Index finger button.
How do I go back then?
You can use the mouse wheel.
Okay, so this is telling us where we find meteorites, and most of the meteorites we find in Antarctica. Those are not available for sale because of an agreement that nothing can be sold that comes from Antarctica, so they all go into universities or scientific study and that kind of thing. But other meteorites that are found, this is where we find them, mostly from farming. So if you want to find meteorites, the best way, be a farmer. And then Antarctica, the reason that we find so many meteorites in Antarctica is, first of all, that because it's like a field of white snow most of the time. So if you see like a dark spot, you just run over there really quick and it's probably a meteorite. And that's true also, a lot of meteorites are found in Africa in the sandy fields where same thing, you see a dark spot and it's probably a meteorite. But the reason we find so many in Antarctica is because of the glacier action. As the meteorites fall onto the snow, the glacier moves them towards the ocean, and if they come up against a mountain range like is depicted here, this would be the base of the mountain range, all the meteorites kind of fall and collect there. And people discovered there was meteorites there, and then they thought it was a fall, and they realized that these are all from different places, and so that's a good collection point. And plus, as they go there, even as they sink down in, the wind is at the mountain range is very high, and so it clears off the top of the snow, and so it makes them really easy to find there. Okay, the types of meteorites, there are 4 different types basically. There's 3 shown here, but the chondrites, chondrites and achondrites are the stony meteorites, so that kind of counts as 2. And then there's the iron, which come from the core of a planet, and the stony iron, which come from the mantle of the planet. And these types have gone through a lot of melting, and the achondrite stony as well. The chondrites have not gone through melting, and it's interesting because scientists and astronomers are very interested because those are the type that really show us what the solar system was like and what planets were like when they first started to form. And we'll be talking about that type more next month. So fall versus find. A fall is when you actually see it fall, and then you locate the meteorite because of that. And a find is when, like farmers and stuff, who just find them. And you find a lot of irons, people can find them because they're magnetic, and they're heavy and easy to identify. This is way different. So when you're finding stuff, you find a lot of irons, whereas this type is not so easily recognized. But the chondrite is really the most prolific type of the ones, you know, when we look at all the falls, that gives us a better representation instead of just like the limitation we have when we're finding them. I should stop and explain exactly what a meteorite is. I think most of us know that. A meteor starts as a shooting star, and of course it's not a star at all. It's a piece of rock or metal, even something as small as a grain of sand. When it's, you know, in orbit around the sun, if it collides with Earth, when it hits the atmosphere, the friction causes the air to ionize. So when you see a meteor or a shooting star, it's actually a rock with the air like burning or actually ionizing as it goes through space. And then if that piece falls, then it's called a meteorite. And the falls can be seen with naked eye, but many of them are also found with camera networks that they have around the world. There's not a whole lot of them, maybe a half a dozen or so, but where they set up cameras in different, where they can get a whole view of the sky, and when they have this kind of, you know, if you just see a meteorite or meteor coming down and from one location, then you see it's like over there, but you have no idea how far away it is. But if you can get it from different points, from different camera sites or from cameras, in addition with visual reports, then you can actually calculate the orbit of that meteorite. And they found several of them. This shows the orbit of the inner planets and the orbit of, I think, 6 different recorded meteorites where they've been able to calculate what the orbit actually is. And they've determined that most meteorites do come from the asteroid belt.
Where do these automatic camera stations, are they planted all over the country, or do you know?
I don't know. I have that in book somewhere. I didn't write it down here.
There is the NASA All-Sky Fireball Network, and they are distributed all over the country. And what they do is they triangulate. They try and get 3 cameras within 75 miles of each other. There are none in Michigan right now. So if we'd like to try and get some of those, that'd be great.
In this cloudy climate, who bloody cares?
So how to identify meteorites? I'm not going to spend a lot of time on this, and none of this information is 100%. These are some clues that you can use when trying to determine if something is in fact a meteorite. One is a sighting. If you see it fall, or if you have camera evidence of it, then and you locate it, then you know you have a meteorite. And if you find it, what they call a strewn field, when meteorites fall, they tend to break up in the atmosphere, And when they fall in pieces, and they fall in an oval shape. And they can either do it one of two ways. Generally, you'll see a lot of meteorites in like the beginning of the oval, or it can be a lot of meteorites in the end of an oval. So if you find something in a strewn field like that, that's a clue that it's a meteorite. They're not crystalline like quartz, or when you see a crystal structure, that's not going to be a meteorite. They're not layered, like if you see sedimentary layers in rocks, that's not going to be a meteorite. Attraction to a magnet. Most meteorites will easily stick to a magnet, but this is not true for any of the stony ones, so none of these, like I said, are 100%. The weight, they are generally much heavier. When I pass these around, you'll feel that for something that this size, people are often surprised how heavy this is. And I'm going to pass around my samples, and if the box is open, then I encourage you, you're welcome to touch them and look at them, and I'm going to pass around some little magnifying glasses too. This one, a loop here, there's a little switch on the bottom, and this one, unfortunately, is a blue light, so it kind of makes a false color. But this one has really nice light in it, and so you can switch that on, and when you look through these, here's how I use a loop. And there's more than one way to do it, but I usually put this right up to my eye, and then you hold this to where it's in focus, and that's how you can look at it. There's another way to do it too, but this is the way I find the easiest. So, but if the box is closed, please don't open it, because that means it's more of a fragile one, or it might be already broken, or it might be a really expensive one. Another indication that something is a meteorite is it has a fusion crust, which can happen as it's going through the atmosphere. It's a thin layer on the outer edge. And when I buy my meteorites, I always try to, I've got many of them that don't have, that have been cut, where you don't see any of the natural surface. But I usually try to get meteorites that have some of the natural surface around them as well. Some of the surface features, what they call regmaglyphs, look like a little thumbprint, and this actually happens when the meteorite is going through the atmosphere. The meteorite itself doesn't burn. It's the air around it, as I mentioned. Of course, rock doesn't burn. It's the air around it that's ionizing. But the metal, if it's a metal meteorite, it can heat up to very high temperatures. But then as soon as it starts to heat up, it like liquefies. And so if you see a trail that lasts for a long time, that's probably because it's leaving this metal trail that as it liquefies, it just falls off the meteorite and is left in the air. So when you see these trails that are lasting, that's often the cause of that. And as it's liquefying, the metal is melting like this, depending on the shape of the meteorite, like if the air tends to like hit something and cause it to sort of swirl around like in a little eddy current of air, it causes these little circle in depressions, which are called regmaglyphs. Many of the chondrites, the stone meteorites, the chondrite type have little bright metal flecks in them, and we'll see many examples of those next month. And the chondrites also have little circles in them that are like little droplets of lava that have solidified. And the word chondrite comes from a Greek word chondrule, which means like a grain of sand or a seed. And so when it has those, there's a good indication that it's a meteorite. The little circle ones don't occur on the planet at all. And the Wittgenstein pattern is a definite, that's one of the things that's definite. If you find this Wittgenstein pattern, it's definitely a meteorite. And I'm going to explain about the Wittgenstein pattern when we get into some of the next slides.
I have a question about this. On number 3 from the top, solid. And then the...
Oh, I skipped that one, didn't I? Normally, if it has holes in it, like a porous material, like lava that you find is sometimes porous, then it's not going to be a meteorite. Meteorites are solid. But that's not 100% true. There are some examples that have these bugs, which basically just means a little hole. What was your question? Did that answer it?
Yeah, what would cause that little hole?
I don't-
Erosion in the atmosphere as it's going through?
No, that's,
Could be the intrinsic nature of the stone itself.
yeah, I'm
Yeah.
sorry, I don't have the answer to that. It might be in one of my
Little,
slides. And
meltable.
when we talk about that type, that's, I'm not even sure what type that is, but
Could that be
That's
something,
it.
it's not homogeneous, there's some portions of it that are, maybe a little less dense, a little, more, prone to, being vaporized by the heat, something like that?
I don't know the answer to that.
Okay.
Sorry, I'll try to find that for next time. Maybe next month I'll have an answer to
Okay.
that one. Okay, so then orientation and the nickel content, we'll see in the next couple of pages here. So if it has this shape, there's two ways that a meteorite can fall, and one is just tumbling with no particular orientation, and then that doesn't give us any clues about the shape. But sometimes they're coming down and they're spinning this way, and that gives you this shape here. Like this is, I don't have any examples of, I'm looking for a meteorite that has a good example of this, shape to it.
Save your money.
I saw one on eBay and I missed it. I don't remember if I bid on it and I lost it or if I missed the bid, but I'm still looking for one like that gives this shape. And this is interesting too, that as I mentioned about how a meteorite can heat up, and when it melts and this part leaves that trail, that's called ablation, like it's losing material. But when a meteorite lands, it's always cold, which a lot of times in movies they get that wrong. I saw something in like a Superman movie or something where a meteorite came down, it was like blazing hot, people touch it and burn it. If you actually burned your hand when you touch it, it was probably because you're burning it from frostbite, because it's been in outer space where it's super cold and it doesn't heat up. If it does heat up, and whatever material that heats up is lost. And then you've got like just the wind going so fast through the atmosphere that actually keeps it cool. And then finally we can know meteorites by the nickel content. When you find like the nickel iron ones that come from the core of planets, are you stretching or do you have a question?
I do have a question. Do you have questions now or at the end?
I'll take some questions. I don't want to run out of time, but go ahead.
I wanted to know, what about the melt patterns? Like, I would expect that if they have the, trademark melted crust, they would have gotten hot on the surface.
But they do get hot, but they don't, when it doesn't stay, that heat doesn't stay. When they land, they're always cold.
It goes through the atmosphere so fast.
It's just at the
It doesn't
surface.
take very long.
The interval of heating is so brief that it doesn't
So
have a chance.
I don't have a
to
lot of
rise.
time, so I'm gonna try to keep questions to the very concise as possible. So the presence of nickel, this is an example of a particular iron meteorite that would come from a core of a planet, where you can see the nickel percent is almost 10%, whereas in typical igneous rocks that you find on Earth, the nickel is is 0.08. So when you find metal, it's like, how do you know, if it doesn't have the Wimmenschneider pattern, how would you know for sure, is it a meteorite or not? And when you find this high nickel content, then that would be a definite that it's a meteorite, because that's not found on Earth. Okay, so the difference between differentiated and undifferentiated. And today we're only going to talk about the differentiated, but I'm going to just describe the undifferentiated to compare that for you. So differentiated is when, like the planet Earth, the body was large enough and therefore hot enough to cause the metal to cause the whole planet basically be heated up, and the things with the lower melting temperature, like nickel iron, will liquefy, and then gravity will cause it to sink to the center. So something, a differentiated body, has gone through a lot of heating and changing, which the chondrites don't. They haven't gone through this kind of heating and changing, which is why they're so interesting, because they you know, this type of a body has gone through many changes, so it doesn't tell us what the planets were like when they first started to form, like the chondrites do. So this is where you get the layered effect, like our planet with a nickel iron core, and then the mantle, which is a lot of olivine crystal, and then the thin crust. Whereas undifferentiated, or the chondrites, they do have some heating where it allows this little beads of chondrules, the little lava droplets, or little beads of nickel iron to form into these beads, but not enough for the whole body to get hot enough for them to, it's not large enough and therefore not hot enough for these to sink to the center. And so it hasn't gone through the heating changes that the differentiated ones go through that we're talking about today.
Right.
So this just tells a little bit about the formation of the planets. When we first started with the solar cloud, the sun forms, and then you've got this solar nebula, this gaseous material surrounding the sun, and they start, little bits of dust and particles start to get gathered together just by static. And once they get big enough to actually have enough gravity, then they can pull other bits together. They're attracted by gravity, and then they get larger. And so the first stage, once they get into a body, is called a planetesimal. And this is what the chondrites, or the undifferentiated, fall into this category. They're planetesimals. And then these bodies they're always like crashing into each other, and when they crash into each other, they may break up into millions of pieces and then gather again later through gravity, or they might stick together and form larger bodies. And once they get large enough, then we call them a protoplanet, which the protoplanet is the differentiated planets like our Earth that we're talking about today. And this is not to be confused with the planetoid or a minor planet, which is basically a dwarf planet like Pluto and Haumea and Makemake and those. In the beginning, I used to use these terms like interchangeably. I thought they all meant kind of the same thing, and then I looked them up and I found exactly. So planetesimal and protoplanets. So protoplanets are what we're going to talk about today. Next month will be the planetesimals.
Right.
So there's a lot of detail in here, and I'm not going to go through all the words here. I just want to show you the basic outline, and then we're going to zoom in on some certain areas as we move on. And this shows the whole breakdown of the different type of chondrites, which we'll talk about again next month. This shows the breakdown of the differentiated material that is the ones we're talking about today. So I'm going to zoom in on just that area. Oh, and this also shows a primitive type. There's actually, this presentation comes in 4 parts, and I have 2 parts scheduled with you for this year, the one I'm doing today and next month for the chondrites. And probably next year maybe we'll schedule the primitive type and the tektites. So those we'll schedule for another time. So I'm going to zoom in on the differentiated part. So that breaks down into 3 main categories, maybe 4 categories, however you look at this. This part is the iron and the stony iron that come from, the irons come from the core of a planet, and then the pallasites come from the boundary between the core and the mantle. And then we have another stony iron, but that comes, they think it's because an iron and an achondrite have crashed together and combined. So that's this category, which I have one example of. And then we have the achondrites that come from the crust area of the planet body, the planet, protoplanet. So I'm going to talk about now the first section. The blue arrow will show us we're going to start with irons. So the irons can be broken down into three categories, which is the hexahedrite, the octahedrite, which is the cool one that has the Rubinstein pattern, and the Tektite that doesn't have enough iron to actually form the Rubinstein pattern, and it polishes this beautiful mirror-like surface. And this is an example of one of those regmaglyphs that I talked about, where the eddy of current, as this was heating up and the ablation caused it to lose material, and so that happens during its path through the atmosphere of the Earth. So the hexahedrite is low nickel, and it can't form a Rubinstein pattern because the Rubinstein pattern, I'm going to talk about that in a little more detail, is because of the differences between the nickel and the iron. And this word here, Pallasites, is a type of nickel iron that is less than 10%. This is nickel iron, but it's high. It has only less than 10% nickel, so it's a higher type of iron, of nickel iron. And then the Tektite, or axatite, as I've also heard it pronounced, is from the Tektite, where it's much higher nickel. And the octahedrite has both of these types of nickel iron. So we'll start by looking at the hexahedrite. And this is an example of the hexahedrite. And it has these Neumann bands, which they kind of look like just scratches in the surface, but this is kind of like the Rubinstein pattern starting to form, where it's just the Pallasites, and as it cools down very slowly, these lines can be formed. And you can only see this when you cut it open and do an acid etch. So the octahedrite was with the Rubinstein pattern, and both of these, all these nickel irons come from the core of a planet. So, and we know those come from outer space because there's only one way that this Rubinstein pattern can be formed, and that is when you have the nickel iron and it cools down very, very slowly, like over millions of years. And we know that, and there's only one way that can happen, and that's in the core of a planet. And we know that the core of our planet is still molten or liquid-like, and so it didn't come from the core of our planet, so it must have come from a different planet, so therefore it must have come from outer space. The Rubinstein pattern is named after some guy in Austria named Rubinstein. Figured out about those. And this first part explains about these, the pattern, the Rubinstein pattern is this lamellae, which are the different bands or the stripes that you'll see, and it's the difference between the Pallasites and the Tektite in there that, as it cools down very slowly, those different types of nickel iron separate and form these patterns, only when it cools down very slowly like that over millions of years. And then the octahedrites can be broken into three types: the coarse, medium, and fine. And that there's a couple of things that we can learn from the Rubinstein pattern about how large the parent body or the protoplanet was. And the larger the bands, the longer it took to cool, which means the bigger the parent body was. And also the nickel content will have an effect on the size of the bands as well. I think it says somewhere exactly what. So now looking at some of my examples, we'll start by looking at the nickel ions, and Something about the Wittgenstein pattern, it's unique like a fingerprint. And in one sense, when you look at a fingerprint, they all look the same, right, the ridges of skin, but we know that each one is unique. And the core of a planet, as it cools and creates its Wittgenstein pattern, they all look very similar, but they're also unique like a fingerprint. And we look at these two, this piece I have and the ring that I have, when you compare these two pieces and look at the pattern, you see the pattern is exactly the same. Some of these other ones, like this one they found in a previous one, they found this one in Africa in 1836. Of course, it landed millions of years ago. We don't know how long ago, but you know, it was basically the Western people found it in 1836. The native people had known about it for much longer. And when I pass around this ring, you'll see that this one is the natural surface. And these two, these are the natural surfaces. There's two natural surfaces sides on this, but it's been cut open to where and done an acid etch so we can see those Wittgenstein pattern. And when you compare my ring, these two together, you'll see that the pattern is exactly the same. And when we look at these, the pattern looks very similar at first glance, but they're not exactly the same. And I had added the picture of my other ring, which this one from Sweden, this ring and this particular piece here, they also match exactly. So they came from the same meteorite. They came from the same planet, the same core of that same planet. And we know that the pattern matches like that.
Is that how you got them all at once?
No, no. This was my very first meteorite that I ever obtained. It was a gift. Got it in California. And the ring here, this one I bought at a rock shop in Ann Arbor called Four Directions.
Sandra, since we're about halfway through the presentation, how much time do you need to let everybody see the sample? Should they be passing them around?
I'm starting to pass them around right now, actually, which is why I'm opening the boxes. I'm going to leave that one closed. Okay. So I'll go ahead and start here. And here's the loop that you can use to look at that. So this one, these are the fine octahedrite. And the one from Sweden is also fine. This one is a medium. This one comes from Peru, which is medium octahedrite, which has thicker bands. And then this one, some jewelry I have, which the jewelry I have, I didn't make this. I bought jewelry that somebody had this meteorite and made it into jewelry. And this has some nice examples of the regoliths in it. They're much smaller, but you can see that. And this was a really interesting event. This was a fall rather than a find, which means they saw it fall. And this fell in Russia in 1947. It fell during the day, and it was said to be brighter than the sun, and it left a trail that lasted for hours. And there's a couple of stamps that they put out on the 10th anniversary, which I have these stamps, and I didn't bring my meteorite stamps with me. I have a small collection of meteorite stamps. I'll bring them next month. And this one, I found this on eBay, where they found some of this type here, which she had Aline, I think is how it's pronounced. And I found this one, which is the same type on eBay, which they're selling for $10,000, which they found pieces embedded in wood that got embedded in trees, which I thought that was really interesting. I didn't buy it, but I just thought it was interesting, so I showed it here. This is one which is, with this high of a nickel content, it should be enough to actually make the Wittgenstein pattern, but they don't really know why, but it doesn't. This is the X-type type, and it doesn't have, it's interesting because it doesn't have the Wittgenstein pattern. It has this like sugar-like structure to it.
Could it get cooled quickly?
Could be.
Or could you go back to that for a second, please?
Oh.
That, actually, you
This one's really small. When you pass around the samples, that one's really super teeny.
okay, thank you.
And then this type is the type that is much higher nickel content, doesn't have enough iron to form the Riemann-Steffen pattern, came from Russia. And I've shown here, as I pass these, I don't, some people often ask the price of these, and they're very varied. You can get pieces which are like $5 and up to $10,000 or very high prices. So you can kind of see the prices that if you're interested, you can kind of pick into that. This one, I haven't found a lot of information about this particular type of meteorite. There's a meteorite bulletin that like is a scientific bulletin you can find for all meteorites, but there's like very little. But I bought this one because this neat inclusion in it. I thought that was really cool. It's kind of a small one too. When you see it there, you'll see how small it is. But you might want to take a point to look at that interesting inclusion. It came from France. So now we're going to move on to the Pallasites. And I'll open some of these. I'm going to leave a couple of these boxes closed, the more fragile ones. So the Pallasites come from the border between the core and the metal. And so they have some nickel iron, and they have some of the olivine crystal, which is part of the mantle. And this name comes from a guy named Peter Pallas, who figured out about these. So this is the first example. I've got two of these that come from Indonesia, and there's just these little bits of metal in it, but you can actually see the Riemann-Steffen pattern in that, which I think is really neat. These are some of the more expensive pieces. And I'll go ahead and start passing this one around. This one is the loop that has a bright light on it, so that you can actually, I put it with these because they're so beautiful. So we end when that gets to 6:30, right?
Sorry, 9:30, yes.
Yeah, okay.
Yeah, we-
So this other type, the Chan, I don't know how to pronounce this one, siderite. If they call it the siderite, if it only has the metal in it, they still call this pallasite. It doesn't, the pattern isn't like a Riemann-Steffen pattern. It has these interesting patterns. And I do have an example. This is the same kind. They call it a shamine siderite if it doesn't have any of this crystal in it, the olivine crystal. And if it does, they call it just a shamine, not a siderite. And you can see the difference in the price here, where these are not cheap, but for 25 grams, $70 for this particular piece, whereas this one for 8 grams, it's $50. And there's a lot of beautiful this examples, and I had added one in the presentation, but I didn't have it in the one that I sent Jim yet. And there's a piece that's about the same weight, 25 grams, it's like $300. But you can see some of these really beautiful ones that have a combination. And this springwater pallasite is a really small piece, which has this combination, just 1 gram for $50 there. And that one's a little more rare. But those are like what they call the stained glass of meteorites. They have these beautiful glasses that you can look through. So then we'll go to the next, mesosiderite, which is a stony iron, but they come from an impact of the iron body and an achondrite body. And they have a lot of iron and silicate in it. And this is the example that I have, the Mondoc meteorite, which,
You might have it either.
oh, I put that in the wrong box. That should go. So anyway, that's okay. That's in the first box. It's a stony iron. I should probably put it in the other box. But that's one of my favorite ones. I think that's really pretty. So then into the achondrites, we'll start with this first category of the HED, which is the, let's see, make sure I pronounce it right here, the Howardite, the Eucrite, and the Diagenite. And we believe all of these came from Vesta, from the asteroid Vesta. And these are what they call breccia, which is a lot of broken fragments together. And let me get these ready to pass around. These, I'm going to open this one, but most of these are pretty small and fragile, so they're not going to. And I'll put a magnifying glass. This one isn't as powerful as the loops, but it doesn't have a light, unfortunately. But I really like these, the breccia formation, which has all these like rocks put together in a matrix. And they have the monomitic and the polymitic, which basically just say whether it has one type of rocks that are put together in the breccia or many different types in the breccia. So the first example, the Howardites, are actually a combination of the material in the Eucrite and the Diagenite material. And I have two Howardites that are both in the same box, and I pass it around. And you see this material, all these different material in a matrix, which that's what they call the breccia. And then this one is my other favorite piece here. And I like all of these, the Eucrites, which, because they have so many different colors put together that you see, and this comes again from the crust of the planet. And this one, you actually see the surface of the crust of this, I should say, protoplanet, not planet, which protoplanet, again, is the type of differentiated planet. And you can see all these different things together in this matrix. And this, we know that this can't come from Earth because these types of formations that you're seeing here would have been destroyed with the things that we have on Earth, like plate tectonics and volcanism, volcanoes, and wind erosion and rain erosion. This would have been destroyed. So we know that these came from planets that do not have plate tectonics and volcanism and
The one
erosion.
on
And
the
so
right here, that's kind of like the moon, some of the moon rocks, similar.
I have some pictures of ones that are lunar, but and so this comes from Vesta, which is kind of like the moon, I guess. And then this is the Diagenite type, which again is a breccia type. And these all are just, slight, this fragmental breccia they call it here. And they have slight differences with the HED, but they all come from the planet Vesta, or the asteroid Vesta. So we'll move to the Angrites, which I don't have an example. These are super expensive. I just have a couple of pictures that I found on the internet that were for sale. For a gram is like $400 or $500. And they're really, really pretty. Oh, this is the type that has little holes in it.
Is there a meteorite exchange that sets prices on these, or?
You can basically sell for anything that you like. I get a lot of them from a place called Meteorites for Sale, and Meteorites for Sale, for each type, they are a set price per gram. Where if they have like several different of these, which both of these I saw listed on Meteorite for Sale, and if you calculate this is the same price per gram. If you use a calculator and find that, and all the ones, but anybody can sell it for any amount that they want to. A lot of them I buy on eBay.
Who authenticates that it's actually a meteorite before it goes on sale?
Well,
I mean,
you have to be careful of that, because when you buy them, you don't know for sure. And so, like, there's a Achondrite that fell in 2013 in Russia that made the news. Was one of those really bright ones, kind of like the necklace one that fell in Russia, that everyone fell in Russia. And there's a lot of little black pieces And I didn't want to buy any of those because you don't really know for sure. But the one I bought has the structure in it that you can actually see that matches, like there are pictures that you can find on the meteorite bulletins that are authenticated through this Meteorological Society thing. And so when you look at these bulletins, those are, but that just tells you about the meteorite. That doesn't tell you, is this specific one of those meteorites or not. And so you have to kind of match the picture and consider the source and such. So then the next example, and skipping the primitives, that's going to be a whole other discussion maybe we'll do next year. But this is the example of Martian, and then this is the example of Lunar, which I showed here. And these also are very expensive. Just 3 grams, $2,000 is one example, and these are both for Meteorites for Sale, .com, I think. And this one, 1 gram is just, $400. So they're very expensive for, and this lunar one, they know that these are lunar or Martian meteorites. So this happened when something like crashed into the moon and bits fell off into space and eventually collided with Earth and landed on Earth. And they know the moon ones just by comparing the samples that they brought from landing on the moon. And the Martian ones they know because there's like little bits of gas that's trapped inside, and then they analyze that gas, and then they can compare it to the atmosphere of Mars, which they have analyzed with spectroscopy. I'm sorry, I can't read. Thank you for that. And where basically what they do is they look at the light and they break it down like a prism, and then they can, when they look at all the details, they can see, basically you can just tell any material on Earth, they do the same thing where they put a very thin bit in like a microscope and they go through with a spectrometer and break out the light where you can see spikes in different areas, and that's how you match what the material is. And so they match this to, they know these pieces are Martian meteorites.
It's amazing. I don't know. Does it make any sense to anybody? The 3-million-year-old crater Mojave, 58 kilometers in diameter and the youngest crater of its size on the planet, has been identified as a potential source of these meteorites. Well, holy Christ! What's going to make a crater that big originating from Mars? Anybody got any
Something
ideas?
half the size of the Chicxulub big impact.
Yeah.
You mean that thing came from... All right, okay.
Actually, I've come to the end of my presentation
Almost had a
here.
heart attack.
This show, I have one scheduled in December of the part 2. If you can't make next month's meeting, you could go to the lowbrows meeting, and I'll be giving the Achondrite presentation again there. The primitive and Tektite ones I'm scheduling probably with you guys sometime next year if you want to have me, and with lowbrows I'll be doing those again next year. And there's also some YouTube videos that you can look at that I've done, where if you look at this particular website, and I'll give, Diane has this presentation, a couple of people have this on their computer, so if you want to get some details, you can ask the people who have it on their computers, and I'm willing to share this presentation. Just ask me to email it to you, and then you can grab these more details if you need it. So those are some, and other ones that are not involved in meteorites. I gave my Lick Observatory presentations that are on YouTube as well. Okay, any questions?
The presentation you just showed us with all these slides, is that available on any website?
No.
On YouTube though.
Hey, Sandra?
Yes.
Have there been any meteors containing other elements? I mean, they're all iron and nickel primarily, you said.
Well, no, the ones that come from the core of the planet are iron and nickel.
Mhm.
The ones that come from the mantle the Pallasites are basically, that show the boundary between the core and the mantle. They have iron and nickel, but they also have a lot of olivine crystal, which the pieces that I passed around, some of them don't. Some of them, which the Siderite, are the ones that are only in iron and nickel. And then there's the type that have those olivine crystals, which the Indonesia ones had very little iron and nickel. And then the Say Chesman or something, I'm not sure how to pronounce it, that one has much less of the olivine crystal. And then the Achondrites have very little nickel iron at all. They're mostly just stone. So what was your question?
Well, if they found other, lead, uranium as an example, these heavy elements sink to the core typically. Gold, even.
There are other things in there besides
but
nickel
not
iron,
enough to really.
but not, yeah,
Right.
let's see if,
Those elements are present, but they're.
this
very
one
small.
shows,
Yeah.
how
Yeah.
small a
Yeah,
bit
there you
of
go.
cobalt and copper are also found in there, and then there'd be even smaller bits of other elements in there as well.
So how many pieces of meteorite jewelry do you have?
The jewelry, I have the earrings and the necklace of the one that fell in Russia. I've got the Siderite that is also from Russia. I've got 2 of those necklaces, so count a pair of earrings as 1 or 2. Let's call it 1. Okay, so that pair of earrings, that necklace, the 2 Siderite, then I actually have 3 rings, which I passed 2 of them around, and there's another one I bought, which is a nickel iron meteorite, but they didn't know where it was from, and it wasn't that expensive, so I bought that anyway. That makes 8. And then I have a Moldavite necklace, and I think that's it. I think there's 8.
Maybe I missed it, that the differentiation between meteorites and tektites.
Tektites I haven't explained yet. Since we have some time, I'll just go through it quickly. A tektite is not a meteorite, but it was made by a meteorite. And it doesn't come from outer space, but it's been in outer space. And what happens with the tektite is when you have a meteorite, but not just any meteorite, a big meteorite, like a really big one, like the kind they think killed off the dinosaurs 65 million years ago. A big one like that, when it comes in, it's coming in so fast and it lands so hot when it lands that it melts the earth. And the liquid earth then splashes into the sky, it leaves our atmosphere, and that's where it goes into outer space, cools down and rains down, and it's like glass, because you know how they make glass, it's like you heat up sand, right? And so when you heat up this dirt, then when it solidifies, you get something like dirty glass, and those are tektites. And we'll have, maybe I'll schedule, if you guys want me, I'll schedule a presentation about those. I have about 30 different pieces of those.
Do you have any of those? No?
No, I don't have any of these. Chocolate.
So I just wanted to make an observation. You corrected something that I had wrong for a long time. It's popularly believed that Pallasites are named that because the first samples came from the asteroid Pallas. And it was very good to learn the truth that it's actually named after a German scientist rather than the asteroid. So the asteroid Pallas does not have any fun glass inclusions that we know of. So
Exactly. This, by the way, is another necklace. I don't think I mentioned this. This is the same material as one of the rings that I passed around, the one that's encased in resin that comes from Sweden. So this is another one. I counted that in the 18 pieces of jewelry I have.
Could you go back to the slide on hexahedrites? I believe it was not too far after this slide. Or was it before? It's fairly early.
No, after that. Look, this one or this one?
Before that.
This one? It
Was it?
shows
No,
the different types.
On hexahedrites specifically.
The next one.
The next one, there.
Yeah, okay. So are those ever polished to make jewelry or?
Probably. I don't have any examples of this at all, personally, jewelry or otherwise.
Any examples that are thought to originate from Venus?
Not that I've heard of it all.
It's too high in escape velocity.
That's what I was thinking.
Much too high.
Yeah.
If I were so doggone old, I would remember when the hypothesis for tektites was that they were from the moon.
Yeah, I heard that.
Oh, yeah.
I remember hearing a lecture on that at the Detroit Astronomical Society, and that was something from the moon, my goodness.
Actually, they thought the meteorites might, before it was thought that they were terrestrial. Nobody knew, in the very beginning, nobody guessed they were from outer space. And then they actually saw examples where and it was thought that these rocks somehow were formed in the atmosphere and rained down. And then came the idea that they came from the moon, which some of them do, but not most of them. And now it's proven that they come from the asteroid belt, basically. Diane?
Yeah, I remember seeing a planetarium show when I was about 8 or 9 years old, so this is the late 80s, and it was presenting 3 different hypotheses for tektites, and I'm not sure how any of them were right.
That late in the game?
That late.
Oh, wow.
Well, you know, I have a book that by this guy, and I haven't actually read it yet. I've got like 8 books, and I've read through 4 of them. And this one, I started it, when I got it, it got wet. It was left outside, and when they delivered it, and so I was prying the pages around. The guy said he didn't believe that tektites were at all what it's described, and I think that he's kind of crazy. I think but I'm yet to read that particular book where he did, nobody knows. You know, he stated that it's impossible for them to actually form the way that scientists have hypothesized, and it's not known for sure that this is the way they were formed.
There's different kinds of tektites that confuses things, or makes it more difficult.
There's tektites, and then there's impactites, which the tektites are the ones that splash up into the sky, and then basically there's the Libyan glass, for example, where they believe a meteorite landed, and it didn't splash into the sky, but it still heated up the sand underneath it and turned it to glass.
They got some particular place to fail, or they fell in Ecuador, for example. They fell any place when they fell down.
The tektites, you mean?
Yeah.
Tektites well, there's different examples, and they fell from different places. I have Indochinites, where it landed somewhere like in the ocean around Australia or something, and the bits fell in Indonesia and China and Thailand. And it's a huge field. This was a huge event. If this particular meteorite had fallen in the center of the United States, these bits, tektites, would have been raining down throughout the entire continental United States and Mexico and Canada. So it didn't land there. They landed, you know, where I said in Asia. But, and then I have the Moldavites, which are from Czechoslovakia. Those are really pretty, the green ones. And then there's the Libyan glass impactites, which are from Libya and Africa, and I've got a few other types as well.
I'm not sure if I'm getting it confused. Did you say some are in the asteroid belt? So not all of them, they don't automatically all have to fall to Earth to be a tektite, that some are...
Oh no, well, tektites aren't from the asteroid belt. Well, meteorites mainly come from the asteroid belt.
Okay, not
so when a tektite is formed, that's when a meteorite fell to the Earth,
right.
And so.
But they always come right back down, or do they stay up there ever? Is that part of the thing? Is that they do come down?
Yeah,
okay.
I'm pretty sure. I don't think
only the ones we find.
Yeah, I mean, I guess it's not impossible that some of them are lost, but I think that the escape velocity, they don't have the kind of escape velocity to lose Earth's gravity.
I think we have time for one more question. Maybe
Anybody
two.
who hasn't asked a question yet? Okay, any other questions at all?
Go for it, Jonathan. I saw your hand.
I was just going to make the observation that one of the popular theories about the extinction of the dinosaurs was that it was actually caused by the sheer amount of Earth matter pulled up into orbit in the vacuum left by the Chicxulub impactor. Because basically that's what produces tektites, is that the meteor coming in actually leaves a vacuum behind it. Really? And that's what draws the molten material up.
We actually don't know 100% sure that the dinosaurs were killed off by the meteorite. Because when you
it's
look
just-
at like, when, they know that a big meteorite happened in 65 million years ago, approximately. It's like plus or minus a couple million years.
But there's
So
also
the dinosaurs
iridium.
could have easily died off like a million years before
They were in
that
trouble.
event happened.
Yeah, that's
Is the iridium layer, are those tektites then?
No.
Did that
The
come from?
spherules, there are spherules of
There's-
glass in the KPG bond.
But the
They're called
iridium layer,
microtektites, that are little, very, very tiny
No,
spheres.
iridium is from the impactor, and then the spherules are from the tektites, and they're found around the world too.
1, 2,
So,
3, 4,
But the
5,
idea is that the glass
6,
raining back down into
7,
Earth actually
8.
heated things up so much that the dinosaurs couldn't.
All right. Well, I think we've had a very entertaining presentation, and she'll be back in October with more. And if Sandra awakened your hunger for a meteorite collection, you can pick one up at Astronomy at the Beach from Jar Meteorites.
You will be there
By the way,
Saturday.
She wants
the
all
choice
the samples.
Jim Mineral fossil show they have every year